Good morning everyone. Welcome to the second session of the second day. I'm Shaily Verma and I will be talking about mathematical proofs. This is the second lecture on mathematical proofs. So you have already attended 2 lectures yesterday on proofs. So today I will just talk about some techniques, some common techniques to prove some statements. Okay. So I'll just listed out some common techniques, proof techniques, and so first of them is like direct proof. So direct proof is that we want to prove some statement, and so in this method we directly go towards a conclusion. So suppose in terms of like symbolic format, so suppose we want to prove that P implies Q. Okay, so you want to prove that so this is a statement of this format: if something happens, then this statement is true. Okay, so in this format you can write this statement in as a proposition like this: P implies Q. Okay, so in this kind of a statement, if you want to prove, so by direct method you just assume that okay, my P is true, P is given to you, and now using this P, you and by making use of the some known results, some known facts, you just reach to the conclusion of Q. Okay, so you directly reaches towards your goal to proving Q. Okay, indirect proof. The another technique is indirect proofs. So sometimes it's not very easy to go for direct proof, getting a direct proof. So we can have indirect proofs where we don't exactly prove the statement P implies Q, but we prove some other statement which is equivalent to this statement. So two types of indirect proof is contradiction and contraposition. So contradiction, yesterday you have seen already, right? Contradiction technique. So what we do in contradiction technique, so suppose if you want to prove this statement itself. Yes, so basically you assume that P does not imply Q. So basically you assume that okay, you have given P and you wanted to prove Q, but Q is not true. So you assume that Q is not true, and then you work with your statement P, and you work with your non information whatever you have, and at some point you will get some contradiction, you get some fallacy, like something which is not possible. So there you will know okay, you started with wrong assumption, and that's why Q is actually not false but Q is true. So that is contradiction method. So another method is contraposition. So in contraposition, so suppose if I want to prove P implies Q, in contraposition I'm not going to prove directly P implies Q, but I'll prove the contrapositive statement of this. And what is the contrapositive statement of P implies Q? Yeah, this is negation of Q implies negation of P. Okay, so we'll prove this statement. So this is and these we'll talk about this, that these two statements are equivalent. So instead of proving P implies Q, we'll prove that negation Q implies negation P, and we conclude that Q is true. Another technique is proof by cases. So here we want to prove some statement, and so altogether we don't prove it at once, but we divide our statement, our hypothesis, into some cases, and we deal with each case individually. So we can use then any technique on each case. Okay, so and the last common method is induction, which you have already seen. So I'm not going to talk about induction in this talk. Okay. So let's start with direct proofs. So in direct proofs, So if you have statement like P implies Q, then in direct proof you, as I said, that you assume that P is given to you and you make use of the known information to you and you prove that Q is true. Okay, let's look at some example for this. So let's begin with this example. So we want to show that if this equation is given to us, then we want to show that either x is 3 or x is equal to 2. Okay, so can you write it in this form? So P is written over here. What is Q? Yeah, so on the right side actually you can have two statements as well. So you can assume like P implies Q and R, or Q or R. So in this case like Q or R, where Q is x is equal to 3 and R statement is x is equal to 2. So you can say that P implies Q or R, one of them. Okay, so we start with a P. So we have this assumption P and we simply solve it because we have the equation, we can solve it, right? So we take the factorization and by factor theorem we know that either x is equal to 3 or x is equal to 2, right? So that means we are done. Okay, this was simple. So let's look at some other example. Suppose we want to prove that the square of an even integer is even. So we want to give some direct proof. So any suggestions? How will prove?
You said for an integer you want to be equal to k, square 2k, and then you get 4k square is equal to 2 into 2k square.
Yes, so basically we start with some even integer and then we'll take the square of it, and that's what we want to show, that that square is also even. Okay, so we can write it as this statement in if then format, because then it is easy for us to see it as in this form as a conditional statement. So we can write it as if n is an even integer, then n square is even. So here so we take our assumption P, which is like n is an even integer, and so if n is an even integer, then we have n is equal to 2k for some k natural number, and so we'll take the square and we get that n square is also even. Okay, and by the way that every statement may not be like conditional, right? Whatever we want to prove, everything may not come in this conditional statement, but still you may have something like P or Q or R, maybe these kind of statement you want to prove, or maybe P and Q or R, something like that you want to prove. So any statement you want to prove, you can use direct proofs, right? So you'll just assume that okay, this is our conclusion, this is the implication part, and you just make use of the already known information. Maybe in your statement you don't have any information, but the known facts and theory, you will use that. Okay. So let's move toward the indirect proofs. So first technique, as I said, that it is proof by contradiction. So we have already seen yesterday, right, that how we prove certain statement by contradiction. So suppose I have statement, conditional statement, okay, P implies Q, and I want to prove by contradiction. So like I said that in indirect proof, we don't prove exactly the statement, but some equivalent statement. Now you know that what you do exactly in contradiction method. So what do you think, what will be the equivalent statement which we are going to prove? P? P does not imply Q, but that is also like P implies? No, but you are again saying implies. Yes, partially correct, like we assume that negation of q. That means negation q is on the left side itself. We assume at the very beginning that q is not true, right? So it should be on the left side. And what will be on the right side? Yes?
Negation of P implies P.
Negation of?
Negation of P implies that P is correct. Basically that the opposite of this is wrong, so therefore this is true.
P or Q?
P, you negate P and it does not lead to Q. You assume that P leads to Q.
No, that's not true. P is true and Q is false. That we assume, or you are, yes. So we assume that P is given to us already, and now I'm assuming extra. I'm taking this extra assumption that Q is also not true. So on the left side, what I have that P and negation of Q. And what will it imply? It gives me some contradiction. So that means it should imply to some statement which is actually not true, which is not possible. So we can write it as, maybe there may be like other statement you can write, but this is one way of writing in logical format. And this is this, P and negation Q implies C, where C is some non-fact. So non-fact basically is which is not possible, which is, you know, which contradicts some known fact or some theory or anything like that, which doesn't make sense basically. Okay, so this is the equivalent statement for this. So let's look at one example. So suppose we want to prove that if n is positive and 6 bar n minus 1 is a prime, and we want to show that n is odd. Okay, so we'll apply this contradiction technique here. So what we'll do? How will we start? Why? This is my hypothesis. This is given to us. Yes, n is even. We want to prove that n is odd, so assume n is not odd. So basically n is even, and let's start. Okay, so n is even, so that means n is equal to 2k for some natural number k. What next? Yes, so we'll just put this value 6 bar 2k in place of n. We have this 6 2k minus 1, and now we have this formula, a square minus b squared is equal to a minus b into a plus b, right? We can just simply use that and we get this factorization. So now what it tells you? Yes, this number has two factors, but what was given to us that this is a prime. So what does it mean? We
have to prove that at least one of the factors is not 62k minus 1 or 1.
One of the factors?
At least one of the factors is not 62k minus 1 or just 1. So you could probably take 60.
Yeah, so basically one of the factor is 1. You have this factorization and you are saying that this left side is a prime number. That means this factorization is not possible, right? So one of them should be 1.
One should be 1, the other.
Yeah. So one of them should be 1, right? So which of them can be 1? Can this number can be 1? No? Why? Because we have. Yes. And on in the left expression 6k minus 1. If it is 1, then. Yes, exactly, because k is a natural number, so for none of the value of k, 6 bar 2k cannot be like 2 is equal to 2. So that is a contradiction actually. So these kind of contradiction you can get. So this is like doesn't make any sense. So that means we assumed what we assumed that was incorrect, and so n is odd. Okay. So again, notice that here as well, it's not necessary to have conditional statement with you. You can prove any statement by contradiction, like possibly, like it may not be easy always, but most of the times it is easy. Okay, so let's talk about another technique, which is indirect proof. Yes? Because the other one, so what about this? Can it be 1?
No, why are you equating it to 1 is what the last.
Okay, so you have this, you are saying that this is a prime number, but you got some factorization of it. Is it possible for a prime number to have some factors? No, right? If you can write it as p is equal to ab, then one of them should be 1, right? So that's what I am doing.
So the smaller number being considered.
Huh?
So the smaller numbers being considered.
No, you have to check both the numbers. So I am saying that, okay, look at 6 power k plus 1. If it is equal to 1, is it like, can it be equal to 1? Is it possible that 6 power k plus 1 is equal to 1? It is not, right? So this is not just contradiction on the one side actually, so it is both things we have to check. So I have checked this one as well, this is not possible, and now this one. So if 6k minus 1 is 1, then again it is a contradiction, because for no value of k it can take like 6 power k compute to 2, right? So that's why it's the contradiction. Okay, so the next technique is proof by contraposition. So in this, what we have is, we want to prove some conditional statement, P implies Q, and we show that instead of proving P implies Q, we prove the contrapositive statement of it, and the contrapositive statement is not Q implies not P. Okay. So what we are claiming is that these two statements are equivalent, and so if P implies Q is true, then this also be true. So do you have any idea why these two are equivalent? Can you? If
then P shouldn't become true. Like that.
Sorry, can you say it again?
Wait. Like, yeah, like the using the truth table.
Okay, good. Yeah, that is one of the things.
Ma'am, so we can say that Q only happens if P happens, because P implies Q. So if Q did not happen in the first place, it means that P also did not happen, because the only way for Q to happen is through P, because P is implying Q.
Yeah, but P may not be true.
That's
Right? It's not necessary P to be true for the, like, for Q to be true, right? So it's not straightforward. Anyone else? So he gave very good suggestion. You can check with the truth table. That is one of the easiest way to check that two statements are equivalent. And because this is a small statement, you have only just two variables, so you can check by truth table. So if you look at the truth tables of these two expressions, so you'll find that actually they compute to the same true values. So their truth values are same for any assignment. So they are actually equivalent, so we can make use of it. So let's look at some example. So first we want to prove that if n square is even, then n is even. So now what is the contrapositive statement of it? Yes. So if n is not even, then n square is not even. So basically, if n is odd, then n square is odd. Now, can you prove this statement? So, by which technique? Yeah.
Set n to k plus 1. Set n to k plus 1 and square. You get some multiple to plus 1.
Yeah, so basically by the direct proof itself, like you will get it. So directly you just take your assumption that if n is odd and if n is odd, then n is equal to 2k plus 1 for some k natural number, and then take the square of it, and what you will get is this expression. So basically you get that n square is also an odd number. Okay. Oh, so basically if you have noticed that I put it this small little box whenever I stopped my proof, whenever I completed my proof. Do you know this box? Okay, so this so one small box we put whenever we end the proof. It represents that okay, you have ended the proof. So this is called Helmholtz box, and earlier QED sign basically it was used to conclude that you have completed the proof, and later now people use Helmholtz box, and this is because of Paul Helmholtz. He started using it, and he's a famous mathematician and good author, like good writer, and he wrote this book, this automathography, I Want to Be Mathematician. You can check some YouTube videos also, some short clips are there, so it would be fun, it is interesting, so you may want to check it. So you can note down the name if you want, you can check. Okay, let's look at some other example for contraposition method. Okay, so we'll prove, next we'll prove that if two integers like a and b are relatively prime, then b and a plus b are also relatively prime. And what is relatively prime? So two integers are, yes, GCD is 1, or like two integers are relatively prime if there is no prime which divides both of the numbers at the same time. Okay, so we will prove this by contraposition. So what is P statement here? So we can have P statement as a and b are relatively prime, and Q is b and a plus b is they are also relatively prime. So these are our P and Q statements. So what is contraposition statement?
P and A are not relatively prime, then
Okay.
A and B also relatively prime.
Yes. So we start with that if part, that if b and a plus b are relatively prime, and now you want to show that a and b are relatively prime. So if b and a plus b are relatively prime, then what does it mean? Yeah, so some sorry, come again.
I assume that P is some n times k, a plus b is n times k, where k is some natural number which is not 1.
Okay, natural number or some prime number.
Okay.
Okay, yeah, any
It
number.
doesn't make.
Okay, yeah, so basically it means that their GCD is not 1 and they have some common factors. So there exists some prime which divides both of them. So there exists some P which divides B and A plus B. Oh, sorry, this not is missing here. Yeah, so this is like a typo. So this is, we assume that B and A plus B are not relatively prime. Okay. Yeah, because we are in the contraposition. Okay, so that means there exists some prime number p such that which divides both of them. So that means there exists some C1 and there exists some C2 such that b is equal to C1p and a plus b is equal to C2p, right? What next? Okay, so what you have, that a plus b is C2p. You also have that b is equal to C1p. So you can make use of that, right? So we'll just put the value of b here, and what we get is a is equal to C2 minus C1 into p. So basically p also divides a. P divides a plus b, p also divides a. So that's what we have shown, and p already divides b, we have assumed. So that means what we get, that a is that the GCD of a and b is not 1. Is it okay? Okay. So that means they are not relatively prime. Okay, so that's, we are done. Okay, so before we move to the next technique, okay, so do you see any do you have any doubts about contradiction and contraposition? Do you think they are similar? No similar?
In both cases, you're doing a proof with an alternate statement, but the kind of proof that you're doing, what you're proving with those alternate statements is quite different.
Yes, but can you tell me if there is any difference between these two techniques?
In contraposition, we prove the contrapositive indirect method. On the contradiction method, we get a contradiction that tells us that our assumption that the statement is wrong. So therefore, we assume that the statement is right.
Yes, and in contraposition?
We directly prove the contrapositive of the statement.
Yes, we directly prove that this is not true actually. If right side doesn't hold, then left side also not hold. Yes, so that is one difference. And anything else, like do you can you use this contraposition technique every time? Like I said that it's not necessary for most of the techniques to use it for conditional statements only. So can you say it, can you think about it for contraposition technique? Is it possible to prove these kind of statement by contrapositive? So I just want you to think about this contrapositive method, what we are doing. Can we apply this method for non-conditional statements? For example, these kind of statements. Is it possible? Any idea? Yes? If you don't have any idea, I think that is not possible. So it is not possible actually, because you see what we are trying to prove. We are taking the contrapositive statement of the conditional statement. So if we don't have any conditional statement, what will take? How will show the equivalence, right? So this is because of the implication, because of the condition, we can use this method. So this is one big difference between these two methods, that contradiction method you can apply on non-conditional statements as well, but contrapositive method you cannot use to prove these kind of statements. Okay, this is one difference between these two. Okay, so let's move to other technique. Okay, so next is proof by cases. So now we have some statement and we want to prove our statement by dividing our result into different cases basically. So we had to show P implies Q, but now we want to prove by cases. So basically we prove something like R and S and T. So basically we are taking some collection of statements, and for each one of them we will show that they implies Q. Okay. Does it make sense? So what do you think, how many why we have taken only three statements on the left side? Is it fixed that how many statements will be there in the left side?
Depend on what P is. So how many cases we divide P into could be the numbers. If you were to state in the 50th
Yes. So basically these statements are corresponding to the cases. We don't know. It depends. It depends on the problem, on the statement, that in how many cases I need to divide my the whole to cover all domain. So this we have to do exhaustively. We should not leave any case. If we want to prove by this technique, then we have to look for every possible case, right? We should not leave any case. So we will divide it into some cases exhaustively, unless we cover everything, and then we prove this statement that this implies Q. So basically for every case basically we are showing that implies Q, right? Okay, so let's look at one example. So the example is the square of an integer has the same parity. Okay. So what is parity? Yeah, so parity means that either it is odd or even. So the statement says that the square of an integer has the same parity. So basically if n is odd, then n square is also odd. If n is even, then n square is also even. That's what we want to prove. So can you, because this is an example for proof by cases, so can you give me cases? What will be the cases here? Yes, so there will be two cases because we have two parities. So from the statement itself, you know now that how many cases you will make. You have two cases, it depends on n, whether n is even or odd. So in each of the cases we prove our conclusion. So if n is even, then n is equal to 2k for some k, and we show that okay, n square is also even. Easy. For the second case, n is odd, and so we assume that okay, now n is some 2k plus 1, and so take the square, and what we get is that n square is odd. Okay, it was easy. Let's move to other example. So next we'll show that x plus mod x minus 3 is at least 3. Okay. Okay, from this side as well, do you have any suggestion? What will be the cases here? Sorry, I didn't hear. There is no mic. Can you give the mic? It's really not audible. Can you take the mic and say?
X minus 3 can either be positive, equal to 0 or negative. So those are the three cases. So when it's positive, it will be, you can just write it as is without the mod. When it's negative, you will have a negative sign in front of the x minus 3. And for 0, x minus 3 equal to 0, so x is equal to 3.
Yes, exactly. So that will be the three cases, because the value of mod x minus 3 depends on the value of x. If x is strictly less than 3, it will give you different value. It will compute the value of 3 minus x. If x is greater than 3, then it will it will compute the value of x minus 3. So based on that, we'll have these two cases, and that x is equal to 3 itself we can cover with one case. So first case will be x is at least 3 in this case, and the other case is x is strictly less than 3. So in the one case it will give us x minus 3, which is like 2x minus 3, and now because we are in the case x at least 3, so we know that this number will be at least 3, right, because twice of x minus 3. Okay, and in the other case it simply computes to 3, right? So this is done. So we prove this, and yeah, this.
Small typo, case 1 is for all x belong to R instead of this thing, for all x.
Oh, in this case, yeah. So because we are in this case, so it's not for all x belongs to R, but for all x which lies in this case. Yeah, thank you. I did not notice this. Okay, that's it, I guess. Thank you for your attention. Now, if you have any questions, you can ask.
Yes, questions.
Previous slide? Yeah. Yeah, question? I have included that in the first case, because then also it will give you like 0 value, so it can be, it's like positive. Where? Sorry, I didn't get it.
Can you once again just tell, let us know, explain it what sir just told right now? I didn't get that.
Okay, so he pointed out that here I have written that this is greater than 3 for all x belongs to R, but it is not true, because we are in this case, so we have extra condition. It's not like at least 3 for all x right now. Okay, so this is for this case. Anything else? Anyone else? Yes? Yes, say.
So, ma'am, but it will be true for all x.
Yes, yes, it will be true. Oh, by chance, like it is like giving you exactly 3 below as well. But yeah, but when we are in one case, we cannot say that for all. That what we want to prove actually. We are in one case right now.
Ma'am, also is it possible to combine this method with the contradiction, not this?
The other method.
Yeah, the place where we prove the negation of this is equal to.
Yes,
Yeah,
actually.
is that possible to combine with contradiction?
Yes, so we can do that. Actually, in proof by cases, what we are doing, we instead of proving our statement at once, we are dividing into cases. So for small chunk of cases, we like values we are proving separately, then for different values we are proving separately. So maybe we can use different techniques to prove each of the cases. So you can apply direct method, maybe by contradiction. So for by any method you can prove the cases individually. It's not a problem.
No, I didn't mean cases, proof by case.
Okay, so how else you can combine?
Yes, ma'am, contraposition and contradiction.
Okay, so
Can you combine them?
okay, yeah, so like in contraposition what we said that P implies Q we wanted to prove, and we take the contrapositive statement of it, right? So we now saying that okay, instead of proving P implies Q, let's prove this. Now how I prove this, it doesn't matter. You can prove this statement by direct method, maybe by contradiction. You can use any method again. So but yeah, you are just showing that these two statements are equivalent. So instead of proving this, I am proving this. Now you can use any method. Okay, anything else? Any more question? Okay, what is okay, so in second case, because x is strictly less than 3, so what mod x minus 3 will compute to? It will be 3 minus x, right, because x is less than 3. So the value coming out from the mode will be actually the value of 3 minus x, because x is smaller than 3. And that's what I have written here, because now I know that x is strictly less than 3. So when I'm just removing the mode sign, I'm just writing that it is like actually 3 minus x, so it will always give you 3.